This is example 11.6b, and we are still working with the gas laws, and now we're going to relate the gas laws that we've learned to using them in chemical equations. And remember, when we're looking at a chemical equation, the coefficients that we see in front of the molecules represent only moles, or number of molecules, of which moles is a measure of the number of molecules being used. And always when we're using chemical equations, we can relate moles to mass, which is measured in grams, by using the molar mass equation, or if you will, or finding out the number of grams needed to equal 1 mole. The conversion factor is the word I was looking for. So as we move through these chapters, there's just a lot to remember, and I cannot emphasize enough that you need to really write down everything so you remember what you're doing. You don't have to copy the problem. I've done that here just to make things easier. Okay, let's get started. To make magnesium hydroxide, a major component in some stomach antacids, hot water vapor is passed over solid magnesium, and they give the equation here. So for two water molecules in the gas form combined with 1 mole of magnesium in the solid form will yield 1 mole of magnesium hydroxide, which is a solid, plus 1 mole of hydrogen gas. And they ask, if 4.50 liters of water vapor at 200.0 degrees Celsius and 4.94 atmospheres are passed over excess magnesium, how many grams of magnesium hydroxide will produce? It's a loaded question. You've got a lot of numbers and a lot of things going on here. So let's just take a look at this a little bit closer. All right. So again, we have 4.50 liters of water vapor. That's water in its gas form. So we're talking about this molecule right here, and it tells us the temperature and pressure, 200.0 degrees Celsius, and the pressure is 4.94 atmospheres. That's the conditions under which this is running, this experiment is running. And it tells you the volume of that water vapor is 4.50 liters. It tells you that we have excess magnesium. So this is our limiting reactant, and it's all of this 4.50 liters is going to react. How many grams, what is the mass of magnesium hydroxide? How much of this is going to be produced if we use 4.50 liters of water vapor under these conditions? And so, and then I've written that down too. We want to know the mass, or the grams, of magnesium hydroxide that are going to be produced. So if we look at what we have here, so we're given a volume, we're given a temperature and pressure. We're not given a second volume, temperature, and pressure, so we're not going to use the combined gas law. We're given grams. We know there's a relationship between grams and moles, so more than likely we are going to use the ideal gas law, which relates moles to volume, temperature, and pressure. So, but how are we going to use that, and what is it going to look like? So again, the equation only relates moles, but we want the mass in grams. And right now, the only information we're given is about water vapor. So we can use what we know and find out the number of moles we have of water vapor. And so again, we can use PV equals nRT, where P is the pressure, V is the volume, N is the number of moles, R is our ideal gas law constant, and T is temperature. And remember, temperature must be in Kelvin, so we're going to have to do some converting here. Remember that our constant, our ideal gas constant R, is equal to 0.0821 liters times atmospheres divided by moles times temperature in Kelvin. Okay, so using the ideal gas law, the number of moles of water vapor can be found, all right, because we have pressure, we have volume, we have the ideal gas constant, and we have the temperature. So we can find now the number of moles of water vapor. And what does that look like? All right. So again, I've just written down so it's easy for us to remember. We have 4.50 liters of water vapor at the temperature of 200.0 degrees Celsius, 4.94 atmospheres. Remember, our conversion to Kelvin is the number or the temperature in degrees Celsius, and we simply add 273.15. And remember, we have this, since we're adding, we want to have the least precise number, and so our least precise number is 200.0. It goes out to the 10th position. This goes out to the 100th position. So we round that to 473.2 Kelvin. And so we simply take that, our ideal gas law, and we put in our pressure is 4.94 atmospheres, PV, our volume, 4.50 liters, and we're going to set that equal to the number of moles times R, 0.0821 liters times atmospheres divided by the quantity mole times Kelvin times 473.2 Kelvin. If we divide both sides by the R and the T, we can isolate our N, and we come up with this equation where we can cancel our atmospheres, we can cancel our liters, and our Kelvin are canceled, and we're left with moles. And so we get a number 0.57220. And remember, there are only 3 significant figures in all of those numbers, so we round this to 0.572 moles of water vapor, or H2O gas, and that's our N. Now, we cannot go directly to determining the grams using the molar mass with this, because we don't care about how many grams of water we have. We want to know the grams of magnesium hydroxide. So when we go back up here and look at the equation, right, for every 2 moles of water vapor that are used, we are going to generate 1 mole of magnesium hydroxide. That is our molar ratio, or our in the equation. Remember, so for every 2 moles that are used of water vapor, we're going to generate 1 mole of magnesium hydroxide. So we can use that information now because we know how many moles of water vapor we have. It's a lot less than 2 moles. So our number, the number of moles we produce for magnesium hydroxide will be much smaller as well. It's not going to be anywhere near 1. So we use the factor label method, right? We have 0.572 moles of water, and we're going to divide that by 2 moles of water, and set that equal to 1 mole of magnesium hydroxide. For every 2 moles of water vapor used, we're going to generate 1 mole of magnesium hydroxide. The moles of water vapor cancel, and that will leave us with 0.286 moles of magnesium hydroxide. It was just simply a division problem. All right. Now, are we done yet? No, we're not done yet, because now we know the number of moles that we have generated in this experiment, but we don't want moles, we want the mass of magnesium hydroxide. That's all well and good, because we know our old trusty friend molar mass. We can find out the mass of magnesium hydroxide in AMU, and that number, if we weigh out that mass in grams, will contain 1 mole of magnesium hydroxide, and then we can use that as our conversion factor to determine how many grams we have if we have 0.286 moles. All right, so what does that look like? All of you should be familiar with this, right? So when we look at our molecule here of magnesium hydroxide, I know that I have 1 magnesium ion, I have 2 oxygen and 2 hydrogen. And so it's 24.3 AMU plus 32.0 AMU plus 2.02 AMU. And so this is for one, this is simply the mass of one molecule of magnesium hydroxide. And all that tells us is that if we weigh out, and of course we have to pay attention to the least precise, right? We're going to round to 58.3. If we weigh out 58.3 grams of magnesium hydroxide, that sample of 58.3 grams contains exactly 1 mole of magnesium hydroxide. We can use this relationship, this ratio, to determine now how many grams we have in this 0.286 mole sample. So we take what we know, 0.286 moles of magnesium hydroxide divided by 1, and then we're going to factor label. So we want our moles of magnesium hydroxide to be in the denominator where they will cancel, and we have 58.3 grams of magnesium hydroxide in the numerator, so this becomes a simple multiplication problem. And we find that we have 16.6738 grams of magnesium hydroxide. However, we only need 3 significant figures, so that rounds to 16.7 grams of magnesium hydroxide. And if we go back up and check our question, right? How many grams of magnesium hydroxide are generated under these conditions? Here it is in word form, right? How many grams of magnesium hydroxide will be produced if 4.5 liters of water vapor at 200.0 degrees Celsius and 4.94 atmospheres are passed over excess magnesium? And we know that we now have that answer. It's 16.7 grams of magnesium hydroxide.